Well, the relative risk, the method of relative risk is a very nice method because it gives you a clear idea of the association, right? So it gives you at the same time the test for if the association that you observe is random or not. And it also shows you the magnitude of this association. And this magnitude is clearly to understand, right? We understand what risk is and what chances are. However, relative risk works only if you have this dichotomy. So if you have yes and no categories, right? Two categories in each variable. What to do if you have more than two categories? Well, that's exactly the job for chi-square test for association. So in this case, we can take our original contingency table and make a test using all these numbers together. This part of the contingency table that we computed using table function, right? That's what is called observed frequencies. And then we will use a letter O in all our slides here in order to define this, right? So this is the observed frequencies. It's all combinations of the categories of two qualitative variables that we observe. But if we assume that we have no association, if we assume that preferences in soda doesn't influence preferences of the fast food restaurants, no association, that's no effect. You remember our default null hypothesis. So this is our null hypothesis, no association between selection of fast food restaurant and preferences about soda drinks. If you assume that null hypothesis is true, right? What we expect these frequencies to be if there is no association. So that's the overall idea. We can compute the expected frequencies, assuming that there is no association between these two variables. And then we compare how far the observed frequencies are from the expected frequencies. And then we can, of course, compute a statistic, and then we can use a distribution in order to define if this statistic is random or not. Okay. So this is the overall idea. So let's compute the expected frequencies. So expected frequency, it's a frequency that we expect to get if null hypothesis is true. So that's the overall idea. So let's compute them. So this is my table of expected frequencies, so far unknown. Let's compute them one by one manually. Well, the idea is following. Look, if we take this combination, for example, BK and Coke or BK and Pepsi. BK is Burger King, right? So you can see that we have 71 people who prefer Coke and 70 people who prefer Pepsi. And we also have 16 people that actually selected Burger King as the preferable restaurant, right? So what does that mean? It means that we can compute, first of all, the proportion of people who prefer Coke. It's approximately 50.4%. This is the proportion of people who prefer Pepsi. It's approximately 49.6%. And the idea is following. If there is no association, then this expected frequency will be 40.4% of 16, and this expected frequency will be 49.6% of 16. So it means that there is no association. The only thing that matters is the proportion of how many people prefer Coke and Pepsi. Let's compute it. So this is number of people who prefer Burger King, and then we compute 50.4% of 16 and 49.6 should be 6% of 16, right? So this is how to compute it. So this is the expected frequency for combination Coke and BK. And this is the expected frequency for combination of Pepsi and BK. So now we can fill it in. And then you can see actually this is the expected value and this is the observed value. This is the expected value and this is the observed value. And they are not far from each other. So from that point of view, what we observe is not very extreme. Of course, it's different. We always will have a difference. But at least based on our visual estimation, we don't see any extreme difference in this case. But let's proceed. So now let's talk about the McDonald's. So the same idea. We have proportion of people who prefer Coke. We have proportion of people who prefer Pepsi. If there is no association, then 50.4% of 71 should be here. And then 49.6% of 71 should be here. That will be the expected frequencies. Again, let's compute them. So the first will be 35.75. The second will be 35.25. And now we fill them in. And now you can see a difference is quite big. Here we observe 43, although we expect 35.7. Here we observe 28, although we expect 35.25. So now the difference, at least the visual difference, is quite large. Is it large enough to assume that there is association? Is it large enough to assume that our initial null hypothesis is wrong? We don't know yet. Let's continue. Final case. So 54 for Sunset Boulevard, the same idea. We compute 50.4% of 54, and that will give us the expected frequency here. We compute 49.6% of 54, and that will give us the expected frequency here. So that's the computations, and now we fill them in. And again, we see the difference. So here you have by 7 larger than observed, and here you have by 7 smaller than observed, right? Again, quite a big difference, at least visually big, right? So these are the two tables, the observed and expected frequencies. You can think about this as this is what you observe, and this is what your model kind of predicts, right? So this is the expectations. It's like, for example, expected average values in t-test or expected predicted y values in simple linear regression, right? So these are the real values that you observe, and these are the expected or predicted values, okay? Now what we can do, we can compare them. How we compare them? We take a difference, right? So because if you take a difference, you will see how far the expected values and the observed values are. And from that point of view, again, the analogies are that these are observed values, these are predicted values, and these are residuals. So how far the observed values are expected from the predicted values, right? You remember what we did with residuals? We took a sum of squared residuals, sum of squared errors, right? That was our way to estimate how big these residuals are. And in this case, we do the same trick, because we are not interested if it's negative or positive. These are the original residuals I show you again. So what we need to do, we need to get rid of this sign. We need simply to take a square of every of this value. So that will be as squared residuals. So here are the squared residuals. So this one is 0.06 squared, right? And so on and so forth. These are the squared residuals. What is the next step? The next step is that the squared residuals, they depend also on how many values you have. For example, this is big also because this number is big, 71. And this is small maybe because this number is small, right? We don't know. So what we can do, we can get rid of this dependence on the numbers by dividing the squared residuals into the expected values. So in this case, I take this and divide to this. Then I will take this and divide to this. Then I will take this and divide to this. This is the way to get rid of this dependence, right? So I will make it standardized or scaled residuals, squared residuals. So this is standardized or scaled squared residuals where we got rid of this dependence on the size of each category. Okay. So that's it. You can see that this is indeed very small, almost 0. This is a little bit larger than 1, and this is even more larger. Okay, so if you look at this one, this number is bigger than this one. But if you standardize, if you scale, you can see that this difference is actually even bigger than this one, because now we also adjust or take into account how big the category is. Okay. So what to do with squared residuals? Well, we can compute statistic. We can accumulate them. We can compute a sum of squared residuals. It's similar to sum of squared errors. So we simply take a sum of all these values, and that will be our statistic. That's the sum of squared residuals. And this is what we know as a chi-square. You remember chi-square, it's a sum of squared random values. And if indeed null hypothesis is true, residuals should be random values. And therefore, this sum of squared residuals should follow chi-square distribution. It's like a sum of squared z-scores, right? And you remember we discussed chi-square distribution in the second block. We know that it describes sum of squared random values, and then we know that it depends only on one parameter. It's degrees of freedom, right? So how many independent values we have in this sum. So let's use it. Well, first of all, the degrees of freedom in this case is number of categories -1 and number of categories -1 in each of these two variables, right? So for example, in Pepsi, we have 2 categories, so we have 1 degree of freedom here. And then in the fast food restaurants, we have 3, so it means we have 2. And then if we multiply them, we will get 2 independent values. So although we have 6 residuals, we have 2 of them only independent. Okay. So that's the degrees of freedom. Now let's do the calculations. So this is the degrees of freedom. This is how the chi-square distribution looks like for 2 degrees of freedom. And you can see that all these chi-square values are possible. So if null hypothesis is true, any of these values is possible. So you can see most of the time it will be between 0.2, sometimes 2.4, sometimes 4.6. And then you can see that the chances getting smaller and smaller and smaller when you go towards this direction, because this is the direction of extremeness. This is the direction of extremeness. And you can see this is the our value. And what we need to compute a chance to get a value as big as we observe, or larger, more extreme. It's this area. So this is the right tail test. So it means that we need to use a CDF function for chi-square distribution and then subtract the area, because CDF function gives you area on the left, from 1. So that's exactly the p-value. Then you can see it's 0.0335. So that's, if you work, for example, I didn't define the confidence level in this case, but if you work with confidence level of 0.95, its significance level 0.05, that in this case we would reject null hypothesis. So it means that there is no statistical evidence about the null hypothesis, right? About the no association hypothesis. Okay. So that's the final results. So you can see the degrees of freedom, the chi-square, sum of squared residuals, normalized residuals, scaled residuals. And this is the p-value for this null hypothesis, right? So remember that null hypothesis is no association, and if there is no association, the chi-square should be 0 in ideal case. That's our null hypothesis. And then we got 6.79. And then the chance next time to get 6.79 or larger, all the null hypothesis is true, it's this one, 0.335. Okay. R has a function that does it, all these tests for us. So this is the function. You can see chi-sq test, right? And then you can see you need to provide not the original values, but the frequency table already, right? So you need to compute these observed frequencies, not this, of course, but the observed frequencies, the O. And then you need to provide these observed frequencies to this function. And this is the results. You can see this is chi-squared, 6.8 or 6.79, exactly what we got with manual calculations. Degrees of freedom is the same. And this is the p-value, it's all the same. So you can see our calculations made manually were quite correct. Okay. And then this, when you make a chi-square test, like in ANOVA, it contains a lot of other outcomes. For example, you remember in ANOVA we could see residuals, for example. The same here. If you make this test, you can also show the observed frequencies. If you write $m observed, where m it's a variable where you save the outcomes of the test too. So you can see that's exactly what we have here. And if you write, for example, $m expected, you will get the expected frequencies. This is exactly what you have here. Okay. So that's actually it. So a chi-square test can be used for any 2 qualitative variables, regardless how many categories you have. This is just a test procedure, one by one. That's exactly what we went through in the previous videos. And remember that it has also limitations. The first limitation is the same as for proportions. You need at least 5 observations in each of the category. If you have 6 categories, you need at least 5 in each. Otherwise, the calculations will not be reliable. And there is one more thing, right? So in this case, we can assume that there is a significant association between these 2 variables, but we don't know the details. We don't know for which categories it's stronger, for which categories it's less strong, and so on and so forth. So we need all these details. You remember it's similar situation as with ANOVA. We make ANOVA to find out if there is a significant effect, and then we need a Toki test in order to see how big these effects are, and so on and so forth. The same situation here. So you need something else on top of this chi-square test for association in order to see the details. So far, we don't know how to do it. And that's exactly what I'm going to talk about in the last video.